My name is Ashley Foreman, and this is my lab report on Lab 1, constant velocity. In this lab report, I observed the motion of a tennis ball moving at the same speed without changing direction. This was a direct observation of Newton's first law, which is an object at rest tends to remain at rest, and an object in motion tends to remain in motion unless acted upon by an outside force. Because the object remained at a constant speed, there was no outside force, and therefore there was no net force. No net force means a constant velocity, and this is further explained with the velocity update formula derived from Newton's second law, which states that the acceleration of an object depends on the net force acting on the object and the mass of the object. If this net force is 0, the final velocity is equal to the initial velocity, and so there is no change in velocity. So in this physical experiment, I rolled a tennis ball across my kitchen countertop in a straight line, as shown in this video. I chose to roll the ball across my countertop due to its smooth surface and therefore a small amount of friction. The system of this experiment was the ball and the counter, and the surroundings is everything else in frame. The only forces acting on the ball, assuming there's no friction, are both in the vertical axis, the y-axis. It is the force of gravity and the normal force. Knowing that these forces are both equal in magnitude and opposite in direction, the summation of these forces is 0, meaning that the net force is 0. In my observed experiment, I plotted this in Tracker, and I tracked the motion of the ball. And so the start time of this observation is 0 seconds. The initial ball position is at 000 meters. The ball's initial velocity is 2.12500 meters per second. And I found this calculating from just delta x over delta t, and I used the second position minus the first position in both time and position. And then the time of the last observation was at 0.4 seconds. And so I plugged all of this data, also including the average mass of a tennis ball, which is 0.057 kilograms, into the code. And so I plugged that in here. I plugged the position, the velocity. I also inputted the last time. And then I also updated the object's velocity with Newton's second law. So I made sure that this was equal to F plugging in F net over the ball's mass. And the ball's position is updated using the ball's velocity and delta t. And so I plotted the observed motion that was shown on Tracker versus this predicted model that I used the code for. And so the slopes of the lines, I used lines of best fit, differ by 0.026 meters per second. And so the smaller slope is the observed data. And so this suggests that there is an outside force that is slowing this velocity down. And so this is shown. The lines are very, very similar, and then it deviates slightly. The observed data slowly has a slower slope. And so this is attributed to the force of friction between the ball and the counter, causing the tennis ball to gradually slow down with a negative acceleration. And so if the axes were changed, the slope of the line would change. And so with the current axes, the ball rolls in the positive direction, making the change in the position vector positive, therefore making the velocity positive. If the axis was flipped, as shown here, and it was moving in the negative x direction, then the velocity would be in the negative x direction. So you can see this in the graphs here. And this is just the magnitude stays the same, so the slope of the line is the same because speed is a scalar. However, velocity has a direction of positive or negative. And so here's the positive and here's the negative. And so a net force of 0 means that the velocity of an object in motion will remain in motion and object at rest will stay at rest as long as there are no forces acting upon it. This means that either there are no forces or that all the forces on an object cancel out, like the force of gravity and the normal force. In the case of the rolling tennis ball, it has equal and opposite push and pull forces, leaving the F net equals 0. So this push is like the applied force, and then this pull may be friction here, assuming the net force of 0. However, in the case of our experiment, the tennis ball had an unequal amount of these push and pull forces, leading to the negative acceleration of the ball, this decreasing velocity. This is a pull force, which is the force of friction. Given enough distance to roll as well as time, the tennis ball would have eventually come to a complete stop. Had there been no outside forces, the ball would forever remain rolling.